Hey everyone, Mr. Newman here, and we're going to learn about three different kinds of functions, and we're going to categorize those functions. So by the end of this, you'll be able to look at either a graph, or an equation, or a table, and you'll be able to say what kind of function it is. So the first function we want to look at is a linear function. All of these make straight lines. The line can go up, or the line can go down. And there are three kinds of equations. The most common one, the one that I like best, is slope-intercept form. That is y equals mx plus b. The reason I like it is because there's the slope, m, and there's the y-intercept, b. It's pretty simple and straightforward. Now, there are other kinds of equations. One is called point-slope form. I just want you to write those down for now. And then standard form looks like that. And we're going to use all of these a lot more in the future, but for now I just want you to be able to recognize them. In my example, I use slope-intercept form, 2x plus 1, and that is also my table. So you see in this equation, kind of compare this briefly to the other examples. Notice there's nothing squared, and the x is not up high. It's not in an exponent at all. It's just down low, and there's no other powers or anything. It's simply a coefficient, something you multiply by the x, and you might or might not add something to it. Now, looking at this table, there's a pattern here. Every time the x, or the input, increases by 1, the output increases by the same amount. So a constant change in x will mean a constant change in y. So we'll go up by 1, go up by 2, go up by 1, go up by 2. This is either a constant increase or a constant decrease, and it's known as a constant rate of change. That is a characteristic of a linear function, is that the table has a constant rate of change. And it might, if it goes up by a different number on the left, it might go up by a different number on the right, but the rate will stay the same. So let's now draw a quadratic function. Quadratic functions make parabolas. I'm going to spell that out real fast. Parabola. I want you to write that out above, right under quadratic there. The parabola can be up or down. That's concave up or concave down. And there are a few equations for this. Notice, first of all, with the parabola, it's kind of curved, but it is not a half a circle because the parabola keeps on going either up and to the left and up and to the right forever, or it goes down and to the left and down and to the right forever. The equations look like this. Standard form is y equals ax squared plus bx plus c. And vertex form is y equals a times parentheses x minus h squared plus k. Notice both of these have an x squared in them. That's what makes something quadratic and makes the shape of a parabola. My example, I'm just going to take the very basic y equals x squared, and I want you to notice the pattern. When the x goes up by 1, the y goes up by 3. Then the x goes up by 1 and the y goes up by 5. Up by 1, up by 7, and up by 1, up by 9. Hopefully you notice the pattern here is that the amount it increases goes up by 2 each time. But that stays the same because it's always going up by 2. So we call this a second order difference. The first order difference would be like this constant rate of change in the linear table. The second order of difference means that the changing part changes. And that's what you want to look for when you're looking for whether something is quadratic or not in a table. All right, let's go to exponential functions. The graphs look like this. Notice how one side goes up and the other side gets really, really close to the x-axis. That is an example of exponential growth, and here's an example of exponential decay. In both situations, one side goes up and the other side gets really, really close to the x-axis. Growth, your equation is this, y equals a times b to the x. And for decay, your equation is this. In both of these cases, you might want to include that b is greater than 1. That's just kind of assumed here for the growth and decay. Now, the example I'm going to use, I want you guys to compare these three examples very briefly. Notice how if x is down low and there's no exponents, then it is a linear equation. If x is being squared, but the x is still in the base, it is a quadratic. And if the x is in the power, then it's an exponential. These two are easy to get mixed up between, so I want you to notice the difference and note those very carefully, all right? Now, the table for an exponential also something different happens there too. On the inputs, they're going to increase at a constant rate, so increase by 1, but the outputs are going to not add, but multiply to get to the next one. So if we go up by 1, we go up times 2. Go up by 1, go up times 2. And that happens every time, so the outputs are not adding something, but multiplying by the same thing each time. And notice how this case, that times 2, that's the base right here, because that goes up by 2 each time. So this, we call it a constant ratio, because the word for ratio means either fraction or, is a fraction, a division problem. So if you divide 4 divided by 2, you'll get the same thing as if you divide 32 divided by 16. Both of those are equal to 2. All right. So now that you can identify what is the constant ratio, you can identify from a graph, a table, or an equation, whether they're linear, quadratic, or exponential, we need to look at, for example, the domains. On a linear function, you can plug in any number all the way to the left and all the way to the right, depending on the situation, but that means you can plug in any real number. The fast way to write this is all reals. Another way to write this is x could be between negative infinity and positive infinity, and the fast way to write that is with the interval notation, the parentheses. The last way to write this is the shortest and fastest way. I just want to show you guys, we're not going to talk too much about the notation, but you can say, instead of writing the words all reals or writing out the lots of infinities, you can say x is in the set of all reals, like that. I'm going to blow this up real big so you can see this. We write x is in the set of, it looks kind of like a backwards C with a line coming out of it. And then the reals is a capital R with 2 lines on kind of like the backbone of the R. So x is in the set of all reals. For the range, most linear functions, as long as it's not a constant, you can have all reals there too. We're going to write all the same stuff, but instead of x, I'm going to put y there, and instead of x, I'm going to put y there. So y could be all reals. Some of the features is it makes a straight line. It has an x-intercept, usually, and that's where y equals 0. It always has a y-intercept. That's where x equals 0. And then there's also a slope, and slope is also known as the rate of change. So that can be found from the table as well as the graph. And it's also, you have probably heard this before, can be seen as rise over run on the graph. I just want to show you this taxi problem because we've been doing stuff like this. A taxi charges $4 for getting into a cab and an additional $3 per mile traveled. How much would it cost to go 12 miles? I know that this is a linear function because it has a constant rate of change. Each mile, it's going to go up by the same amount. The equation for this, $4 plus 3x, because 3 is the rate of change per mile, that's our equation. You can see it's a linear equation there. I'm going to solve it real fast. If I plug in 12, f of 12, I get out 40. All right, let's move on to quadratic. The domain is the same as linear because you can plug in any number you want, any x value, from all the way to the left to all the way to the right. The range, however, depends on whether you have a concave up or concave down graph. If there's a minimum in the graph, the range is everything greater than or equal to the minimum. If there's a maximum, then the range is everything less than or equal to the maximum. And just to give you a picture of that, if there's a maximum, you see the maximum is right there. The range is everything below that. And for minimum, the range is everything above that point. So, some of the features, we have a vertex, that could be a maximum or a minimum. That's that very, very end of the cap of the parabola, okay? We also have concavity is another feature of the graph. It might be up like a cup, or it might be down like a frown. And that is just a quick little expression for you to remember and see. The blue is up like a cup, and the purple is down like a frown. We also have x-intercepts, and those are also known as zeros, and you also have y-intercepts. All right, an example problem might be something like this. Mr. Newman shot a basketball from half court. The height of the basketball in feet as a function of time in seconds was that right there. What is the height of the ball at 2 seconds? Well, to figure it out, I'm just going to plug in 2, and you get 0.4 feet. All right, for exponentials, again, same deal with the domain. You can go all the way to the left and all the way to the right. The range, however, is everything greater than or equal to 0. Or sorry, strictly greater than. There's no or equal to because of this thing called an asymptote. The asymptote is a dotted line which doesn't actually exist as a part of the function, and it's something that the function gets really, really close to but never actually touches. So that's the only feature I'm going to write in this box. That's a line that the graph gets closer and closer to but never actually touches. Now, the example problem, we have a petri dish. This is an example of bacteria growth. This would be exponential growth. A petri dish starts with 100 bacteria, and the bacteria doubles every hour. The function for the number of bacteria, b of x, after x hours is b of x equals 100 times 2 to the x. What is the number of bacteria after 5 hours? Well, I'm going to plug in 5. b of 5 is 100 times 2 to the, not x, but I'm going to replace it with 5 to the 5th. I can type that in a calculator and I get 3,200. So there's 3,200 bacteria after 5 hours. All right, thank you very much for watching, and we'll see you in class.